Yeah, hi and welcome back everyone. I hope you had a good week and set up your Python environment last week, because today it will be pretty relevant. We will be using your Python environment pretty heavily. So today I will be talking about scientific computing in Python. For that I will be mainly discussing the NumPy library, which is an array computing library. And then in the next lecture, in lecture 5, I will be talking about scikit-learn, which is a machine learning library for Python. So why are we doing that? Why are we spending so much time on computing? I really think it's helpful to have a tool like Python where you can toy around with certain ideas and algorithms that we learn about in this course. So after these two lectures, after the NumPy and the scikit-learn lecture, we will be getting back to the concepts and discuss certain concepts around machine learning. So we will start by decision trees, ensemble methods, and then talk about model evaluation. And it will be very helpful to have a tool like Python where we can try out these things in practice. All right, so with that, let me then get started. So this week I also don't have any lecture slides. I will be using a Jupyter notebook to show you some of the ideas, because then I can also show you the actual code and the code output, and you can have the Jupyter notebook afterwards. Actually, I will make it available now before you watch the video, so that you can actually execute it alongside. And also I encourage you, while you're watching the video, pausing the video once in a while and then also toying around with some of the code that I'm showing you. I think that really helps deepening your understanding of certain concepts. Okay, but with that, I think before I make this introduction longer than the lecture itself, let me get started. Yeah, before we start, I should again mention that this Jupyter notebook is also on GitHub. So if you go to our class's GitHub repository here, it's under lecture 4 and then this IPython notebook file or Jupyter notebook file. So if you click on it, you can also view it, and you can also then download it from GitHub. I will also include this link on Canvas, so you don't have to search for it, but you can maybe just download the whole GitHub repository, or if you recall how to clone a GitHub repository, you can just update your GitHub repository by a pull, git pull. And so that is where you can find the notebook. Something else I wanted to say is, this first lecture will be about NumPy, and you can also find more information about NumPy on the main NumPy website, because the notebook that I created here is just a very basic introduction. So if you want to learn more later, you can also consult the official documentation here, which has all the necessary details. And there's also a learning page. So here the NumPy community compiled a lot of tutorials, from beginner tutorials to more advanced tutorials, which is something you may want to check out later, but for this class it will not be required. I don't think we will cover anything that really goes beyond the basics that I created here. Also, if you're interested and find a bug or something like this, this is the official NumPy GitHub repository. But I would only recommend to file a bug, for example, or contribute a feature if it's really a bug and you made sure that no one else filed it yet, because you can see there are 1,900 issues here on GitHub. So the NumPy community is very busy to not add more to their work. Please, before you submit an issue, make sure that it's really an issue. So you can also, if you have some issues, you can search here for these types of issues. Anyways, the NumPy project is an open source project also. There are many people contributing to it, mostly scientific researchers and people doing scientific computing at various companies. So 1,200 contributors right now. And what's also interesting to see is the code breakdown of this repository. So you can see the majority of code is in Python, as you would expect, but some of the code is also in C and C++ and Fortran. And that is because NumPy is using those primarily C under the hood to make it more efficient. And that is why it's so attractive for Python users, because it is way more efficient using NumPy for scientific computing compared to the basic Python methods or basic functions implemented in Python. Okay, so let me switch one more time to this main notebook here, and then I will briefly tell you what this the first video will be about and what will be covered in the next videos. So I recently discovered this very nice plugin for JupyterLab. So just before we go through this list, it's called JupyterLab Talk. Talk stands for Table of Contents. So if you want to install that, you can go to this GitHub repository and they have some instructions for installing it here. So yeah, you can install it, and then after you install it, you will have such a nice button here, which gives you a table of contents for the whole notebook. So using this table of contents, just to briefly tell you what we are going to cover, in this first video, we are just covering the basics of NumPy. So that means I will introduce what NumPy is, give some little motivation of why NumPy is cool, and then introduce n-dimensional arrays, like the basic data structure implemented by NumPy. And then in the upcoming videos, we will talk more about array construction and indexing, and then also some NumPy array math and the so-called universal functions. After that, we will talk a little bit more about broadcasting, which is a really cool feature in NumPy. And then also some advanced indexing, which is usually called fancy indexing. Yeah, but there's more. There are random number generators, ways for reshaping NumPy arrays, and NumPy comparison operators like creating selection masks and so forth. And then just briefly about linear algebra with NumPy. After we've covered all the NumPy stuff, I also want to give you a brief introduction into Matplotlib. I won't be talking much about SciPy because SciPy is a library that implements some algorithms on top of NumPy, algorithms that are commonly used in scientific computing. For example, the L2 norm that we covered in the KNN lecture would be a function implemented in SciPy. However, SciPy, you can think of it more as a collection of tools, so we don't have to learn anything specific about there. If we need it, I can tell you what we have to import from SciPy, and then we can use it. We don't have to really memorize the whole library. Any case, and then I will lastly show you some Matplotlib. So Matplotlib is a library for plotting graphs. All right, so that is just the overview. It's hopefully not getting too long in terms of time. It looks like it's a lot, but I think we get through this pretty efficiently. Yeah, so let me hide my table of contents and focus on the main notebook now. So like always, I start by importing the Watermark library. So Watermark is a library that I developed just for showing package versions, because personally I find it very helpful to see what libraries I used the last time I executed a notebook. So by that I can make sure that I execute the notebook with the same libraries if I need to reproduce some code, or I can also see whether libraries are outdated or not. So if you don't have Watermark installed, this is what you can execute to install Watermark. And then once it's installed, we can check the versions of the libraries here. So NumPy, SciPy, and Matplotlib, these are the main libraries for this notebook. And yeah, I will be using NumPy 1.19.1. I also recommend that you have a recent version of NumPy. It doesn't have to be 1.19, it could be NumPy 1.18 or something like that. It's actually 19, not 19. So in many open source projects, people count the versions as follows. So the last number is usually a patch version. That means, or let me start on the left hand side. The left number is the major version. So this is NumPy version 1. And then this is the secondary version. It's like this is like for defining the main API. And once the API is stable, there may be some enhancements and stuff like that. And that will be usually the second version number. And this whole numbering scheme is also called semantic versioning. In any case, so this would be NumPy version 1, 119 to be precise, and the number after the second dot, it's just a patch version. So when people release numbers that are greater than 1 here, it usually means a patch. So here, for example, this would be Python 3. Python 3 versus Python 2 is a big difference, a big API difference. And then over the course of the development of Python 3, there were new versions developed. Like they added, for example, the F strings I talked about and so forth. So this is like for adding major features, but they don't change the API fundamentally. And this is like for patching it if there's a bug, but you don't want to make a new version of Python. I mean, it's the same version, you just want to patch the bug, then you add this number after the second decimal point. Any case, so if you have not installed NumPy and SciPy, you can install it using this command with conda. And if you do that and these numbers are still not matching, you can update your your NumPy, SciPy, and Matplotlib versions via conda. So sometimes this will not do anything if you have it already installed, but it may be an old version, so you may have to run the update to get the most recent version. So yeah, I just want to say, make sure you have recent versions here, and then you shouldn't have any problems executing the code from this notebook. Okay, but that was just the setup. Let's get started with the main parts. Yeah, I have a lot of text here. I don't want to just read it out loud. I just want to briefly give you an introduction, like what NumPy is and what it is about. So NumPy is an array library. So it's mainly for computing with computational arrays. And an array, you can think of it as like a tensor. It's actually a data structure for representing a tensor. There are other libraries like TensorFlow and PyTorch. They call that tensor right away, although in technical terms, a tensor is more like a mathematical object and an array is a data structure representing this mathematical object. And the NumPy array is basically the same thing as a PyTorch or TensorFlow tensor. NumPy itself was created a long time ago in 2005 by merging NumArray and Numeric, which were two computing libraries developed approximately in the 1990s. I think Numeric came first, like in the 1990s, and NumArray was a re-implementation of Numeric, and then they diverged a little bit but had different features, and then at some point they were merged. I think it was primarily by Travis Oliphant, who was a big contributor, or still is a very big contributor to NumPy and the NumPy ecosystem. And many other libraries nowadays are built on top of NumPy. Actually, I don't know. I mean, there are probably not many libraries anyone would know that are not built on top of NumPy. So the most notable ones are SciPy, Scikit-learn, Pandas, and so forth. So they are all built on top of NumPy. And specifically, they use the NumPy array format, which I mentioned before, like the multi-dimensional arrays in NumPy, and these we sometimes call them also n-dimensional array, and the short version, the data type, would be ND array, which stands for n-dimensional array. And like I mentioned before, when I showed you the GitHub repository, NumPy is mainly implemented using C code. So Python acts as a glue language around the C code, and that is what makes NumPy so efficient. So NumPy is way more efficient than, let's say, using Python lists, because NumPy uses contiguous blocks of memory. With memory I mean random access memory. That's the computer memory. And that allows things like caching. Like the CPU has like a L2 cache, and it can buffer certain values in the cache and make the access much faster. So in a Python list, everything in a Python list is a pointer to a memory location where the object is stored. The advantage of having a Python list is it allows us to mix different types. So we can have a string type, an integer number, a float, and so forth, everything in the same list. However, accessing it is relatively slow. Of course, if you would execute Python code, you as a human wouldn't notice it looks super fast, but in scientific computing, if you do a lot of computations, this would be super slow and a major bottleneck. And NumPy, it has the downside that everything has to have the same size in an array, so you can only have integers or only floats or only strings. You can't match them in the same array. However, the advantage is if you have only data types of the same type in the array, that means you know the size of that array. So if you have, let's say, 64-bit integers in that array, and you have 8 64-bit integers, you know the size of the array is 8 times 64. And also you only need to store the first memory address, the memory address of the first element, because you can get the other memory addresses by simple arithmetic. So you can just count. So you can say, let's say the first memory address is, at position 16, and the second one would be at 24 because it's 16 plus 8 if we have an 8-bit array. So I was just assuming 8 bits right now. Anyway, so it's an advantage for computational purposes to have everything of the same type. It may be an inconvenience when we work with certain data sets. However, note that this is in practice also not a big problem, because in practice we can also use NumPy when we process, pandas when we process the data, and then we can later convert it to a NumPy array for very fast computing. Another thing I wanted to say is, besides being more efficient, one other advantage that I really like about NumPy is that it allows us to implement code more elegantly and makes it also more readable. So that's mainly the linear algebra operations that we will see later. And also coincidentally, there was just a paper about NumPy released after all these years. The community finally wrote a review paper. So that was it was last week. So it was published in Nature, and it's called Array Programming with NumPy. So here's a figure from that paper that again highlights that NumPy is really like the foundation of the Python ecosystem. Also, you basically have even foundational libraries built on top of NumPy. So NumPy arrays come at the very bottom, and then on top of it you have Matplotlib, the plotting library we will be talking about, and scientific algorithms that all use the NumPy arrays. And then you have technique-specific libraries such as scikit-learn, the machine learning library that we were talking about in this course. There's pandas, and stats model, a statistics library, and so forth. And there are also domain-specific and application-specific tools. So everything, like you can see here, is kind of built on top of NumPy. So NumPy is probably the most influential or most important Python library. For example, just recently, when the first black hole was discovered, the pictures were taken, also NumPy was involved, in Matplotlib and so forth. All right. Yeah, but before we get started with a bottom-up approach, where I will show you the different things in NumPy, I wanted to give you a brief motivation why NumPy is cool. So what I did here is I just provided a very simple computing a dot product. So I'm not sure why this is missing, doesn't matter. So this dot product here between two vectors, between a vector x and w, can also be expressed by a sum, basically a sum over these products here. So you have x1 times w1 plus x2 times w2 and so forth. So you can express the dot product also as a sum. So here I was just spelling it out. That's the long way to write this. And every time you see a sum in Python, every time you see a sum, you can convert it to a for loop in Python. So a sum, how I would code it up, I would use a for loop, for example. So this would be the naive way of implementing this dot product. I would write it in Python. So assume I have two lists. One list is A and one list is B. So 1, 2, 3, and 4, 5, 6. So the computation here in this function would be 1 times 4 plus 2 times 5 plus 3 times 6, which I think should add up to 32. So if I would execute this, let's check. Yeah, it's 32. So this would be the naive way of computing a dot product in Python using a list. So using lists here, and then the for loop iterating over the elements in the list, and then adding them to this output value, which we then return. That's our 32. So recall the timeIt function from last lecture. So I'm using here the timeIt function to time how efficient this function is on two larger arrays. So we have two arrays with 1000 elements each. So let's execute that. Yeah, that takes a while. That shouldn't take that long. There we go. Okay, so yeah, that is executed in 96 microseconds, or let's say 100 microseconds. Now I have the same thing in NumPy. So here it's the dot product in NumPy. I can write it like this. Here it's a NumPy function, but you can also call a method directly on an array. It doesn't matter, it's the same. And this should give us the same computation. Again, a dot product, it's like a linear algebra vector dot product is 1 times 4 plus 2 times 5 plus 3 times 6. So it should also be 32. Just to double check, it generates the same results. And now let's time how fast this dot product is in NumPy, and then we can compare it to the Python implementation. La la la. Okay, finished. Yeah, this one runs in 1.6 microseconds, 1.06. So it's about 100 times faster than our Python implementation, which I think is pretty impressive. Yeah, and if you recall from the KNN lecture, I showed you a way you can compute matrix multiplication using just Python for loops. So we had these two nested Python for loops. So after watching lecture 4, it might be interesting if you could try to benchmark the matrix multiplication in Python that I implemented in the KNN lecture and compare it to using NumPy for the dot product. So in NumPy, there's also a dot function that the same dot function can also compute a matrix multiplication, as we will see later. I think it was in a later video, I will also show you some linear algebra stuff. I think I had it in 4.9. So after watching these videos, it would be cool if you on Piazza could post a benchmark between the matrix multiplication in Python and NumPy, because I think it will be magnitudes faster. This one, the dot product, was 100 times faster for the vector dot product, but I think for matrix multiplication it might be 1,000 or 10,000 times faster. Okay, so that was hopefully some motivation showing you why NumPy is cool. I mean, it's faster, like you've seen here, but also this one is way more concise, of course, than this one, right? So if you have a lot of code, it can actually improve the readability. Oh, one thing I should maybe mention is, so in newer versions of Python, I always forget this. See, I made this notebook and also forgot about it. In newer versions of Python, you can use the @ symbol here, and this will also act like the dot. So @ and dot is the same. So in NumPy, NumPy dot is the same as the @ symbol. So if I replace this by the @, this should also work. Yep, see? So it's another cool feature of Python or NumPy. You can make it even more concise. Although it's maybe arguable if this looks nicer than this. I don't know. But anyways, let's talk about n-dimensional arrays. Yeah, like I mentioned before, a NumPy array is somewhat similar to a Python list, except it has a fixed size and it can have only elements of the same type. And but in contrast to a list, a NumPy array can have multiple dimensions. So a regular Python list is just a one dimension. If you paid attention in the previous section, you've seen that we used one-dimensional arrays, but let's just do it again. So let's do a list. Oops. And then this would be a one-dimensional list, so it would correspond to a one-dimensional array. So this would be, we can also say this is a vector. If we work in the context of a linear algebra application, we also just call this vector instead of array. It's a one-dimensional array. Yeah, and we can make two-dimensional arrays. A two-dimensional array, you can think of it actually as a list of lists. So we have a list that contains two sublists, and that would be a two-dimensional array. And yeah, this is corresponding to this two-dimensional array. And so the array has two axes because it's a two-dimensional array, and Python starts at 0 indexing in contrast to R, so we always count from 0. So in NumPy there's a concept called axis. So the first axis, axis 0, corresponds to the first dimension. And the axis number 1, so this is the second axis because we started at counting at 0. So the second axis corresponds to the second dimension of the array. So the second dimension, if you think of a matrix, in a matrix we have usually, we refer to a matrix by rows times columns, right? So if we write the dimensions of a matrix, it's like so. So we would write it like this for a matrix of type real. The type and dimensions, we would write it like this. Let's say n times m dimensional. So this would be, I think it should be math BB. Always confuse these two. So This would be n rows and m columns. And similar in NumPy, we have x is 0 for the rows, so 1, 2 rows, and x is 1 for the columns, so 1, 2, 3 columns. So this would be a 2 by 3 matrix. Yeah, and then I will talk more about indexing later, but if we want to, let's say, quickly demonstrate what the axes are for, if you're doing indexing, everything before the comma refers to the first axis, and everything after the comma refers to the second axis. So this one would refer to the first axis because it's at the first position. So maybe let's choose some, oh, it's fine. So let's say we have 1 here. In the first axis would be axis 0. We would be looking for index 1 in this first axis would be 0, 1. So we are in the second row because we started indexing 0. And then we look at the second number. The second number would be indexing over axis number 1. So we count 0, 1, 2. So this one should actually return the value 6. Yep. So it was just a quick demonstration of what the axes mean, basically. But we will talk more about indexing with a square bracket later on. So it was maybe a little bit too early to introduce it here. Yeah, NumPy infers the type automatically from Python. So upon construction. So before we had an integer array. So by default, if we converted it to this array 2D, this one here, this will be automatically also a 64 integer array, because in Python, most people, I think, nowadays use a 64-bit computer. So you also have a 64-bit Python installation or operating system also. So this one should be also, so if you use a 64-bit machine, this should also be by default a 64-bit array, integer array. However, you can convert it. So I'm for some reason converting it directly to a float here, but you could convert it into integer 32 array. For example, you can do s-type numpy int 32, and this should be a 32-bit integer array. And you can also convert to other data types, like from integer to float. So you can use this float data type. You can do a 32. You can also do a 64 and convert into other types. And you can do the conversion by using this s-type command here. Yeah, why is that useful? It's not necessarily useful here, but if we work in deep learning, that's the other class I'm teaching, Statistics 453, where we use PyTorch, we usually work with 32-bit arrays or tensors in PyTorch, because GPUs just work better with 32 bits. It's more efficient, basically. It uses less storage, but one downside is you lose precision. So by that, what I mean is if you have, let's say, a number like, I don't know, let's say 1.001. So, oh, sorry, too much. So if you have this number here, this is a 64-bit float. So you get this precision here. But if you convert it to a, let's say, 16-bit array, you will lose a lot of precision. I mean, it will use less storage, so you will use only 16-bit instead of 64-bit, but you will use a lot of precision. So if I execute that, you should only see 1 point, because it doesn't have the precision to show so many points after the decimal point. Yeah, see, so you would have to remove a lot of these. So yeah, this would work, but if you have more, it gets basically cut, because it uses less storage, so it cannot represent the same number of precision. So in scientific computing, I highly recommend that you use 64-bit integers. However, in deep learning, there's a lot of randomness and stochasticity and stuff like that, so precision doesn't matter that much. So 32 is also fine, and some researchers started working on 16-bit algorithms that work well with 16-bit, but here in this class, yeah, please use 64-bit integers or 64-bit floats. Okay. Somehow my Jupyter Notebook is stuttering. Sometimes I click and nothing happens. I don't know what's going on here. Anyways, and ndim. So yeah, ndim, this is showing us the number of dimensions. So recall we had a 2 by 3 array. So there are 2 dimensions, x is 0 and x is 1. So this should return a 2 because we have 2 dimensions. So if we have a big array, lots of numbers, and this command may become handy, especially if we have like a 3 or 4 dimensional array. It's sometimes hard to see. So this is just a quick way of accessing the number of dimensions. However, I actually rarely use that command. I usually almost always use .shape. So .shape is giving you the shape of the array. So you can get 2 types of information. So if you do something like this, length of that shape, this would correspond to ndim basically. It would be the same as ndim. And here, if you just do it like this, it gives you more information because it tells you how many elements are in each dimension or axis. So this tells me there are 2 elements in my first dimension. So there are 2 rows, 1, 2, and there are 3 rows, 3 columns, because there are 3 elements in my second dimension. So 1, 2, 3. So I usually almost always use shape, and if I actually need the number of dimensions for something, I always use, for some reason, length. Shape is just a habit. I never really think about ndim, but it's there if you need it. It's probably more efficient to call ndim than this one. All right, so yeah, that was a lot of stuff about introducing NumPy. In the next video, so I will make a short cut here, and in the next video I will talk about NumPy array construction and array indexing.